Okay. Hi everyone. So my name is Edgar. I'm a second year PhD working for the National French Center of Research. And my work is based on developing new deep learning tools that automate tasks for ecologists, basically. One of those works are based around making a new image detector that would work for detecting any kind of arthropod. So, as you probably know, we kill a lot of insects while trying to monitor them, which is kind of a bummer. So, one thing we would try to make this better is to avoid it as much as we can. And so, one of the options for that is using less destructive traps. And one way to avoid one way to make non-destructive traps is to use camera traps. And this has a lot of implication about how much data processing you need to have afterwards, because camera traps tend to produce a lot of data that you need to process. So computer vision has a key role for that. So you could split this task into two tasks, although I'm putting segmentation aside. So you have image classification, which is basically when you go down to the species, identifying the species that is on the image. That's cool. That's something that we have a lot of data for now. So you have a lot of platforms that are collaborative, such as observation.org on iNat. And it is even, as somebody already said, it's on GBIF also centralized. So we have a lot of data for this. What we're lacking though, there are way less or way scarcer amount of data for insect detection, which is knowing exactly where on the image the insect is, because you need detection for many tasks. For instance, if you have two species on the same image, you cannot use image classification. Classification only outputs one label, so you wouldn't be able to identify multiple species. And even if you have multiple occurrences of the same species on the same image, classification only gives you the info of the label, so you don't know how many species there are on the image. So it's really bad when you want to assess for insect abundance, for instance. So we settled to try to fix this by making our own datasets for detection. Of course, we have limited resources, so we have to make choices of what we annotate. And so we went for this plan right here. So it's an iterative process, meaning we do it multiple times. So we start by scraping data from iNaturalist. As we did not have much resource, we settled for only arthropods, so insects and terrestrial arthropods, meaning insects and other groups such as spiders, for instance, that were located only in France, because that would be already enough data to annotate. And so each time we scrape a new batch, we annotated it via a deep learning model, which was YOLO 11, I think. And so once the data was pre-annotated by a deep learning model, it was not perfect because the model was not trained at all on insects. So we had to correct it by hand. But then you start to have data to train the model on, because you have manually annotated data. So we could basically feed the model back its own images and train it again. And so we did that multiple times, adding more images, pre-annotating them with a slightly better model, and then correcting the data and feeding the model the new images, and so on and so forth. And in the end, what we got is a data set that is, so here's a representation of this data set with a taxonomic representation, where you can see it's all arthropods, and you see how it's balanced. So that's about 40,000 images that were annotated from iNaturalist. So here are some examples of what you can get from this. It was about 22 iterations, and that's about 600 families of arthropods that are actually present in France. And for those interested in precise metrics, we try to assess how good the model was actually. And so we had also all sorts of test sets for this. And we also assessed how good models perform depending on their size and heaviness. So because the end goal is to use smaller models directly in embedded systems, whereas bigger models should probably be used only as a post-processing manner. So the way we should see this is that mostly we could reach satisfying results by reaching at the 90% mark for F1 scores for most models. And for the second graph, you can, it's about how well the model actually generalizes. So we took other species that were not present in the training set and tried to see how the model performed. And it was quite nice at generalizing for other images, of course, from iNaturalist, because you still have the bias of the kind of images you get from iNaturalist. And so we had a good generalization for other species as well as species that were not present in France. So here, for instance, we measured for South American arthropods. For the future, so we're currently testing our model in embedded systems. So here's a so-called tent malaise, so malaise tent or malaise trap, which is one kind of tent that you deploy to trap flying insects mostly, and they have to go into one unique output. Generally, you would kill them at the output by using liquid like alcohol. And here we're trying to avoid this by using a device that's powered by solar panels and batteries, and that actually lets the insects go through. So you just flash them like with a camera, and you try to identify them. And so our goal here is to make a compromise by detecting the arthropod inside directly the embedded system. So we only save images where there are actually important things to save. So it lasts longer outside, basically. And afterwards, we have the saved images where we know there are arthropods, and we plan to classify them with bigger classifier that could not be used in the embedded system. So that's it. Thank you.
Thank you very much. Last speaker.